Our power grid, it's literally the backbone of our modern lives. But it is facing a huge, huge challenge. How are we going to build a grid that can handle this massive shift to renewables and EVs without, well, breaking? It turns out some engineers have this really wild new way of planning for it, and we are about to dive right in.
Forget about planning for your average Tuesday. No, the real question we should be asking is this. What if we could design a power grid that actually simulates, anticipates, and builds defenses against its own absolute worst day before that day ever even happens?
Okay, so to really get why this new solution is so cool, we gotta first understand the problem. And as it turns out, our entire electrical system, well, it has a fundamental identity crisis. So picture this. Our world is basically built on two totally different kinds of electricity. On one side, you've got alternating current, or AC power. That's the old school grid, right? The spinning turbines, the stuff that powers all our heavy industry. But then on the other side, you've got direct current, or DC. That's the language everything modern speaks. Your laptop, solar panels, the battery in your EV, it's all DC. And here's the kicker. These two systems, they don't naturally speak the same language. So every single time you plug your phone into the wall, that little power brick is converting AC from the outlet into DC for your battery. Now multiply that simple act by billions of devices, solar panels, and electric vehicles. All of that constant converting, it adds up to a staggering amount of wasted energy. So the brilliant solution to this is what's called a hybrid AC-DC microgrid. You can think of it like a smaller, smarter, local power grid that has dedicated highways for both AC and DC power. This lets them work together perfectly, which slashes all that conversion waste. It's really the grid of the future. But, and this is a big but, this awesome new design comes with a really dangerous hidden flaw. Right, so that leads us to the next major piece of the puzzle. See, in solving one problem, we've kind of stumbled into another, and this one's a lot more dangerous, the threat of extreme instability. Now check out this quote from the research paper. It talks about a lack of rotational inertia. So what on earth does that mean? Well, the old grid had these massive, heavy, spinning generators. They had real physical momentum. Think of like a heavy spinning top that's really hard to knock over. The new grid, though, it's full of lightweight stuff like solar panels and wind turbines. It's more like a featherweight spinning top. Super efficient, yeah, but way, way easier to knock over. And that fragility, it has a name: transient instability. Okay, so just imagine for a second a tiny disturbance. Maybe a cloud just passes over a big solar farm, or there's a sudden dip in the wind. In one of these low inertia grids, that tiny little flicker can spiral out of control in milliseconds, creating this catastrophic wobble in the system's frequency that just brings the entire network crashing down. That right there is the grid's hidden enemy. And this is the paradox, right? It's kind of ironic. The very technologies we absolutely need for a clean energy future, I'm talking about wind and solar, they're what we call inverter-based resources. To put it simply, they don't have those big, heavy spinning parts. They connect to the grid using smart electronics, and that is precisely what makes them part of this low inertia challenge. And look, this isn't just some theory on a whiteboard. Back in 2016, during a blackout in South Australia, the grid's frequency dropped at an absolutely insane rate of 6.25 hertz per second. That is an incredibly fast collapse. It's a real-world, terrifying example of this wobble in action. So what does that mean in terms of money? Well, get this. The cost of just trying to prevent a total blackout in a situation like that can be as high as $55,000 per megawatt hour. This isn't just some inconvenience. It's an economic catastrophe just waiting to happen. So how do you fight an enemy this fast and this destructive? Okay, so this is where it gets really clever. You don't just go out and build a stronger wall. No, you play war games. Engineers are literally designing an enemy, an opponent whose only job is to break the system so they can learn from it. You have to realize this is a total change in how we think about this stuff. To create a grid that's truly unbreakable, you can't just design it to work perfectly on a sunny, calm afternoon. You have to build it from the ground up to survive total chaos. So how do they do it? They use this framework called the Defender-Attacker-Defender model. It's basically a three-step loop. Okay, step one, the defender, which is a planning algorithm, designs the most cost-effective grid it can. Then step two, the attacker, another algorithm, goes on the attack. It throws every possible worst-case scenario at that design, trying to find the one perfect storm that will cause that catastrophic wobble.
And finally, step 3, the defender takes all that failure data and redesigns the grid from scratch so that it's immune to that specific attack. It's this constant loop. Break it, rebuild it, break it, rebuild it, all happening inside a computer simulation. So what you've really got here is two AIs locked in this strategic battle. One is the architect, trying to build the perfect system. The other is the saboteur, relentlessly searching for its single point of failure. And by letting that saboteur win over and over again in the simulation, the architect figures out how to build a grid that, just can't lose out in the real world.
And believe me, the attacker's toolbox is just brutal. It simulates everything: a massive instantaneous drop in wind power, an unexpected spike in demand, a critical piece of equipment just failing out of the blue, or even the microgrid suddenly getting cut off or islanded from the main grid. Basically, it's the ultimate stress test for any disaster you could possibly dream up. But, of course, building something this tough, well, it's not free. And that brings us to the final and, honestly, maybe the most important takeaway of all: the real-world trade-off. So when the researchers actually crunched the numbers, the result was pretty undeniable. You can see it right here in this chart. A grid built using the stability-driven war games approach has a higher upfront investment cost than one planned the old way. To withstand those worst-case scenarios, it just means you need beefier, more robust gear to handle it. And that right there is the core trade-off we're all facing. So do we go for the grid that's cheaper up front, one that's optimized for a normal day but is really vulnerable to those rare catastrophic events? Or do we spend more now for a grid that's genuinely tough as nails, one that's designed from its very DNA to survive its absolute worst? So, as we're looking at this future that's going to be powered by clean but variable energy, this question, it's not just for the engineers anymore. It's for every single one of us. It really boils down to this: how much is that guarantee of always-on power worth to you?